Hello, I'm Patty Simpson with Simpson Math. Let's talk about hypothesis testing. The first step in performing a hypothesis test is to identify the alternative and null hypothesis. So let's do that now. Let's identify the alternative and null hypothesis for a few scenarios. First of all, a hypothesis test is just a technique for testing a claim about the population parameter using statistical principles. And the alternative hypothesis, we denote with a capital H and a subscript A, is a mathematical statement about the parameter, and it's the hypothesis that the researcher is aiming to gather evidence in favor of. It's also called the research hypothesis. And then the null hypothesis is the mathematical opposite of that alternative hypothesis. It's always going to include the equality and the equal sign in there. And this null hypothesis is always assumed to be true. So you can kind of think of it as if you were in a courtroom and you had a defendant, you just assume that that defendant is not guilty. That's your automatic assumption. Until proven otherwise, he's not guilty. And the same thing is true with the hypothesis test, that the null hypothesis is assumed to be true, unless you can gather enough evidence to show that that alternative hypothesis could be true. So this is kind of like that person in the courtroom. You're going to assume that they're not guilty. Here we're going to assume our null hypothesis is true. And then if you happen to gather enough evidence to show that you see guilt without reasonable doubt, well, that's the same thing with our alternative hypothesis. We're going to gather enough evidence to show that alternative hypothesis might be true. So that's kind of the idea of the hypothesis testing. And the first job is just to find the alternative and null hypothesis. So let's do that for a couple of scenarios. Here we have a manager of a candy manufacturing plant claims that since his machinery was overhauled, the mean weight of the chocolate produced is smaller than the correct mean weight of 4 ounces. So he thinks that his chocolate is not producing enough. The machines are not producing enough chocolate. So his alternative hypothesis is that that mean weight is less than 4 ounces. That's his alternative hypothesis. So this just denotes that alternative hypothesis. He thinks the mean is less than 4 ounces. Well, if his alternative hypothesis is that the mean is less than 4 ounces, then your null hypothesis just takes that and it's the mathematical opposite. So instead of being less than, it's going to be greater than 4. And the null hypothesis always includes the equality. So it's greater than or equal to 4. So here's our null hypothesis there. So our alternative is that it's less than 4, and the null is that it's greater than or equal to 4. So remember that when we go out and we collect a random sample of at least 30 chocolate bars, and we weigh them, and then we find that mean of those chocolate bars, that mean is part of a sampling distribution that is approximately normal. And the mean of that sampling distribution would be the same as the population. So we would expect it, if the population mean is 4, then we would expect our mean of the sampling distribution to also be 4. Then we created those confidence intervals where if we go out 68% confident, we'd be going out 1 standard deviation. If we're 95% confidence level, then we'd be going out 2 standard deviations. And if we're 99.7% confidence level, then we'd be going out 3 standard deviations. So, with that confidence interval, if I then go out and grab a sample of the chocolate bars and I weigh them, I would expect that weight, that mean, if the population parameter, if the mean weight is 4, I would expect that mean weight of my sample to be within 3 standard deviations of this mean. If, however, I get some value way out here, then I can start to think to myself, that's really curious, that's weird. So that's kind of the idea of this hypothesis testing, that we're going to assume that our null hypothesis is true, that we're going to get some value in here. And if we get some value in there, then we're going to go, well, it looks like, we don't have enough evidence to show that the machine is doing something different. But if when we get our mean, our value is way down here, it's out, 2-3 standard deviations out, then we're going to go, hey, I've collected some evidence to show that it actually is less than what it should be. So, if I get some value, depending on my confidence level, if I get some value out here, then that would let me know that's some evidence showing that it's a little bit less. Let's do another example where we find that alternative and null hypothesis. So here at Northwest Mississippi Community College, syllabi for an online class states that students should expect to spend 10 hours a week doing coursework for each 3-hour credit class. The director of e-learning for the college is concerned students are being required to spend more than 10 hours per week doing work. So here the e-learner thinks that the mean is supposed to be 10 hours per week, but the e-learner director thinks that it is more than 10 hours. So that mean, that average amount of time that they're spending, the director thinks is greater than 10 hours. That is our alternative hypothesis. Then the null is just the mathematical opposite of that. So here this was greater than, so therefore the null would be less than the 10. And the null always includes our equality. So that is the null hypothesis, is that it is less than or equal to 10. So again, we are going to assume that this is true, that the average amount of time that they're spending is less than or equal to 10, unless we gather enough evidence to show that, hey, that might not be the mean after all. And the way we're going to do that is we, again, know if we go out and collect a sample, random sample of at least 30 people, we know that that sample mean is part of this sampling distribution, and that sampling distribution should be approximately normal. And the mean of that sampling distribution should be the same as the population mean, our parameter. So it's part of this normal distribution, something like this. And then, one standard deviation out if we have a confidence level of 68% of the time when we go out and collect a sample mean, it would fall within one standard deviation. 95% of the time when we go out and collect a sample mean, it would fall within 2 standard deviations of the mean. So depending on our confidence level, tells you how many standard deviations we go out. Then we're going to say, well, I've gone out, I've collected my mean, and I get this mean that is here. Well, I kind of expect that. 95% of the time, I expect to get a sample mean within 2 standard deviations. But if I get a sample mean way out here, then I go, there's something weird about that. Something weird's going on. That's not it can happen. It could happen, but that's evidence against that 10 hours per week. Let's try one more example. So after learning that Peter Collet of Switzerland could hold his breath for 19 minutes and 21 seconds underwater, a group of students decided to conduct their science fair project around the amount of time an average adult can hold his or her breath. Part of the group found research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. So there's this understanding that adults, our parameter mean is that adults can hold their breath for 30 seconds underwater. The other half found evidence to suggest that the mean time is different if the water temperature is cooler. The group would like to test this claim about adults holding their breath in cold water. Now, notice in this one that they didn't tell us if they think they can hold it longer or if they can hold it shorter in cold water. It just says that the mean is different than that 30 seconds if it's in cold water. So to show that mathematically for our hypothesis, our alternative hypothesis, we're going to say the mean is just not equal to that 30 seconds. That's their hypothesis, their alternative hypothesis. Then the null hypothesis is the mathematical opposite of that. And it always includes the equality. So in this case, if my alternative hypothesis is it's not equal to, then the null hypothesis is that my mean is actually equal to that 30 seconds. So again, what are we going to do? We're going to go get a group of adults, put them in some cold water, have them hold their breath, and time them. Then we're going to find the average, the sample mean of that group. That sample mean, if I've collected a group of random sample of more than 30, should be part of a normal distribution, that sampling distribution. So, and I would expect my mean to be about 30. So here's that normal sampling distribution. And just as before, if I go out, 68% of the time, I expect my sample mean to fall within 1 standard deviation. So it could be out here a little bit, it could be out there a little bit, that's normal. We expect that 68% of the time. Even 95% of the time, we expect it to come out 2 standard deviations. So if I get a sample mean that's somewhere out here, it doesn't show me evidence that that 30 is not true. So I wouldn't go around rejecting my null hypothesis just because I get something a little bit out here. I kind of expect that within a 95% confidence level. And then 3 standard deviations out, is 99.7%. But if I get something way out here, well, then all of a sudden I start thinking maybe that mean is incorrect. Or if I get something way down here, then I start thinking, something's a little bit weird. Maybe the mean is not 30 seconds, because that would happen so rarely. It could happen, but it would be evidence against that 30 seconds. So that's kind of what we mean, that beginning part, our piece of doing a hypothesis test. The first thing we have to do is just determine what is our alternative hypothesis, and then from that, what is our null hypothesis. Math made simple at Simpson Math. Thanks for watching.